Here we're going to do a little bit of a review of some of the things we've talked about already. We're going to then go beyond that and talking about enzymes. So let's get started. You've seen this already, and what we're seeing here is that we have a chemical reaction with reactants over here, and the reactants have a certain amount of energy within them, which are contained within bonds. So if we think of this like food, then sort of we can think about it as how about how many calories that those foods might have, because the calories in part is really related to this idea of how many bonds there are and what's the energy value of those bonds. So the reactants, if you take food and you break it down, you're going to get smaller products down here at the end. And in the process, you're hoping that you'll release energy that you can use. Reactants, though, are stable in general, and so in order for them to react, we need to put them in an unstable state. So that's what we say right here, is somehow we have to get these reactants to this kind of transition state in order that it will move forward and form these products. And so we're going to talk about that. So there's just a bigger version of that. So this on this y-axis, you can see it says free energy. And really what that means is available energy. So how much energy is available in these reactants? And then at the end of the reaction, how much energy is either released or is available within the product side. Okay, so this is your activation energy barrier, sometimes called energy of activation, meaning that it's this quantity of energy that we have to, or the barrier that we have to get over in order for this reaction to proceed without any problems. So it's moving it from a stable state to a state where it's a little less stable, and then it's going to move forward. But it will move forward. So this kind of reaction, we're going to see why that happens. So again, metabolic pathways. So we take in food, we break it down, we can get some useful form of energy out of it, usually as ATP. Some of that energy may not be useful, but it may be lost as heat. In the end product, we produce lots of little building blocks to make other stuff. And then we go the other direction, and so in this anabolic pathway, we're going to have to add in energy to create larger, more energy-rich molecules at the end. So one thing that can help this whole process move more quickly is to have enzymes. And you understand this now, that we can lower this barrier, this energy of activation barrier, by having an enzyme that can help facilitate this chemical reaction and act as a catalyst. So it doesn't matter if there's an enzyme or not, in the sense of we're going to get the same amount of energy and products released at the end, but it's just much more readily done, and the rate can be much quicker when an enzyme's involved. So we can see, though, on this graph, so that when we just looked at it, it looked like a downhill slope, and it is. Over here, though, it's kind of the other way. So here we're taking lower energy reactants. They don't have as much energy available, but we're going to take some of them, and we're going to build something. So we still have to overcome activation energy barriers. As a matter of fact, we have even larger ones. So we're going to have to add energy in on this side of the equation. And usually that energy is in the form of ATP. And then we're going to produce some products at the end which have a higher energy value within those bonds. So we can do that with an enzyme. We can do that without an enzyme. But it would be much easier with the enzyme. So sometimes, and in general, these types of reactions don't go forward unless you have something that is both an enzyme and energy being put in. So these two reactions they have these names, and one is exergonic. So an exergonic reaction is one in which the products have a lower amount of free energy or available energy than the initial reactants. Energy is going to be released on the product side, And this reaction is considered spontaneous. The other side is looking at the other way, right? So here we have to add energy in with the reactants to get to the products. And this is a non-spontaneous reaction called an endergonic reaction. Now, a measure of that is to use this equation called Gibbs free energy equation, that will kind of give us, if we see what these values are for Gibbs, then we can know whether or not this would have been a spontaneous or a non-spontaneous reaction. So let me explain. So Gibbs free energy measures these factors. H, which is enthalpy, which is just saying what's the change in the total energy of that system. T, which is the temperature of the system, which for us is usually human body temperature, unless we are sick. S, which is the measure of disorder, how many molecules are there and what's sort of their energy value. And so that is entropy. And so we can use this equation to determine whether or not our actual reaction is going to have a positive number for this delta G, or a negative number for this delta G, and then what does that tell us? So don't want to elaborate on this. I've already talked about this a little bit. Here's just some more definitions. We can define again just a kind of way to look at enthalpy. So where's the internal energy in a system? So, you know, we're looking at how much energy is in the reactants versus the products when we look at enthalpy. That has to do with bonds breaking and reforming, how much energy is needed how much energy is released in breaking bonds, how much is necessary in reforming the bonds. And so that's kind of the sum total of that is enthalpy, right? All right. I don't think you need to worry about this because really what we want to look at is just the sort of the final effect. But here we have this idea of enthalpy again. And so if this change in enthalpy is a negative number, then what we know is that energy was given off. So there was actually this was an exothermic reaction because it took more energy to actually cause the reaction to move forward, and then we find that energy in the reactants. Then we find in the products. So let's just kind of let this one go for a minute. We're going to come back to these ideas of what if this means that the system has lost energy, this delta H, in terms of lost energy when the reaction has taken place. And this is the opposite, that the system has actually gained energy, endothermic energy, is gained by the products. And more energy is gained by the products than the energy needed to break down those or to change those reactants. So entropy is the other piece of it, and that's called delta S. That's what that symbol is. And that has to do with an increase in disorder, like that messy bedroom defense I talked about earlier. So basically, you kind of look at something as on one side of the equation is it kind of ordered. So here are reactants on this side. We have 1 molecule of glucose and 6 of oxygen. And then we look at the product side and we see, oh wow, we got a lot more molecules over here. And these two in particular are kind of low energy value, carbon dioxide and water. And this is what happens to some of that energy. It gets captured into these 36 molecules of ATP. So disorder is increased on the right-hand side. We go from 1 very ordered molecule plus these 6 oxygen to a lot of molecules. And that these two in particular are low energy value. So we see an increase in entropy. So back to this equation again. We measure so if we have a lot of entropy here, that delta S is a high number, or an increase. We multiply that by temperature, which is always going to be the same in the body. We're going to get then a bigger number. So the bigger the delta S is, the bigger that this is, which means the more we're actually subtracting from the enthalpy value, which means the result is going to be a negative number over here. So this could be negative. So this delta G would be negative. So when we see a negative number over here, that's going to indicate that we have an exergonic reaction happening. So it's a spontaneous reaction. And that this says this a little bit more clearly. So if we see that the number that's associated with this delta G, the available energy, is lower than zero, that means, oh, sorry, I'm not reading this correctly. If this number here, delta G, is 0, then the reaction basically is at equilibrium. If delta G is greater than 0, sorry math teachers, then that's a positive value, right? And that means that this is a non-spontaneous or an endergonic reaction. And then the final one is if it's a negative value, so delta G is less than 0, then we're seeing something that is spontaneous and exergonic. And so here, if you're looking at this, it sums that up for us. Exergonic reaction, delta G is going to be less than 0. Endergonic reaction, delta G is greater than 0. And that's important to remember. So finally, this isn't finally, but I'll just run out of time soon. An exergonic reaction and an endergonic reaction, these are called coupling. This is coupled reactions. So exergonic reactions, which are catabolic, release energy, and one of the products of that is ATP, and then the body can use, or the cell can use that ATP to produce larger structures in endergonic reactions, do anabolism. And that's going to use up some of that ATP, so now we've got a lower energy form, ADP, and we've got to reestablish that for, whoops, I didn't mean to do that, for the next thing. So this is energy coupling, meaning that the energy that's released by this catabolic side of these reactions is used then to fuel these anabolic ones. So we need these both to happen in order that we can get energy and we can build things. That's energy coupling. Here is the source of energy that most of us are aiming for when we do those catabolic reactions, and that's ATP. And we've talked about this enough, but the energy is located, like in all things, but in these high energy bonds. So here's what an enzyme can do. Here's the active side of this enzyme. Here's its substrate, which happens to be sucrose. Notice the enzyme is sucrase. Sucrose can fit in that active site. Water comes in. Remember, hydrolysis splits apart these two components of sucrose, and now we end up with the two monomers, glucose and fructose. So that's what the enzyme's actually doing. You can see this sort of illustrated right here again. Now what the enzyme does, so here's the substrate in the active side of this enzyme. Notice what happens here. There's a little bit of tension put on it. So this was the induced fit model I talked about the other day. So not only does the substrate get picked up into this active site of the enzyme, but then the enzyme sort of snuggles around it and puts some tension on the bonds here, so it helps to facilitate the reaction going forward, whatever that forward is. And here you can see there's a strain put on it, and there is just a much more realistic look at this. Would be like the actual, all the amino acids that have formed this enzyme, and here we can see these substrates that are found within there. So just again, another way to look at it. And I think I'll quit right there, and then I'll go on to more on regulation. So there you go. Just what you needed, one more.